Hello class, this is day 20 of Coronachem. Today's assignment, which we're going to review, or yesterday's assignment, which we're going to review today, is a question on page 738 from the practice exercise. It says calculate the pH at the equivalence point when 40 milliliters of 0.025 molar benzoic acid is titrated with 0.05 molar sodium hydroxide. There's a couple things happening in this problem because you're assuming that you've reached the equivalence point, so that means the amount of base that is added has to equal the amount of moles of the benzoic acid. So here's the benzoic acid, here's the ionizable proton, this is benzoate, that means it's missing its ionizable proton, and what you're trying to find is how many moles of benzoic acid there is. So 40 milliliters times 0.025 molar. You can use the equation N is equal to the molarity times the volume, and you're going to find that 0.025 moles per liter times a volume of 41 thousandths of a liter gives you 1.00 times 10 to the minus 3 moles. So we need that much moles of base, and that's the calculation I do here. I use the same formula, the number of moles, N is equal to the volume times the molarity in this case. And so how many milliliters is what we're looking for of this base, which is 0.05 molar, do I need to achieve equivalence, which is the same as 1.00 times 10 to the minus 3 moles of the benzoic acid. So we do that calculation here. We find it takes 20 milliliters of this solution of base to achieve equivalence with that number of moles of benzoic acid. So now the total volume is going to be 20 plus 40. So the solution is going to be 60 milliliters of that many moles of benzoate as well, because if you had that many moles of benzoic acid, once you fully neutralize it, you'll have the same number of moles of the benzoate. So that many moles of benzoate in 60 milliliters of solution gives you I skipped over the concentration calculation, but what you get is a concentration of 1.6 recurring times 10 to the minus 2. Let's just double check that. So 1.0 exponent negative 3 divided a total volume of 60 milliliters, so divided 0.06 of a liter, 1/60th equals 1.6 recurring times 10 to the minus 2. So that is the correct concentration of benzoate anion. I skipped over a step here. So what I'm setting up here is the benzoate in the presence of water will reconstitute, oops, let me readjust the angle so you can see what's going on. All right, so this is the concentration of the benzoate anion because I've produced this many moles of it because it was the same as the number of moles of benzoic acid. So when this is fully neutralized, you're going to have that many moles of benzoate in 60 milliliters of solution. How do I get 60 milliliters? Because you had 40 milliliters at the beginning and you added 20 milliliters of base, so the total is now 60 milliliters. 40 plus 20. So if you take that many moles divided by 0.06 liters, you get a concentration of 1.6 recurring of the benzoate anion. The benzoate is a weak base because it's the conjugate base of a weak acid. So it is a weak base in its own right. So when you mix it with water, you're going to reconstitute benzoic acid and it's going to produce some hydroxide. What did I do over here? I calculated the Kb of benzoate. So the Ka of benzoic acid is 6.3 times 10 to the negative 5. I put it over the ion solubility product of water, so Kw divided Ka is going to give me Kb, and that 10 to the negative 14 divided 6.3 times 10 to the negative 5 gives me this number, 1.58 times 10 to the negative 10. That's our Kb, which we're going to use to set up this equilibrium to find the concentration of hydroxide. So we'll let X equal the amount of hydroxide that forms, also it'll be equal to the amount of benzoic acid that is reconstituted. Kb is equal to the concentration of hydroxide that results. times the concentration of benzoic acid that forms as a result of the protonation of benzoate, and this is the amount of benzoate that remains in solution. And that all equals to 1.58 times 10 to the negative 10, x squared over 1.6 to the minus times 10 to the minus 2 minus x. It gives us a trinomial. We enter the values into the quadratic formula, which I did in my calculator for sake of convenience and brevity, and we get a POH of 5.78 because the value of x, the one we keep, there's two values that are generated by the quadratic formula. One of them you keep, the other one's a negative value, so you discard it, you can't get a negative concentration. This is the hydroxide ion concentration that results. POH is equal to negative log of hydroxide concentration, and you get a POH of 5.78. Subtract that from 14 and you get a pH of 8.21. That was 738A. I'm not going to do B because it's going to be too time consuming. You can try that, see if you get the right answer. And the answer is already there, 5.28, but it doesn't show you the work. But if you can get the answer, there's a good chance you got it right. The next issue I wanted to show you for today is solubility equilibria. The only thing is that finding it increasingly more difficult to erase the board. So I'm going to try to erase it now, but something has happened due to the continued reapplication of alcohol on the surface of the board. It's made it stickier to the marker, and so it's getting harder and harder to take the marker, the dry erase off after I've used it. I'm having to use stronger and stronger solvents, so something is happening to the surface and it's becoming so that you have to really actually work at it to get the dry erase off. It's not coming off easily at all. I mean, if I try to just dry erase it, literally dry erase it, it doesn't. Hardly puts a dent in it. So something has happened. I put in an order today for a dry erase board. A nice cheap roll-up one that's 2 feet by 3 feet, so that'll be better than using a refrigerator, as you can see. See, on the old surfaces, there must be some kind of coating of dirt that helps, that's coming off and taking the ink with it, or maybe cooking oil, or who knows what. But on the really clean surfaces, the dry erase is sticking. So since I've cleaned it several times already, the upper part of the fridge is very hard to clean any further, whereas the surfaces that haven't been used are a lot easier to clean. Maybe I should put some kind of film on the surface of the fridge before I write on it. Okay. And the last thing is to use alcohol to hopefully get the last bit off. Might have to just fast forward through this part of the video because watching me erase is not very educational. Okay. That'll have to do for now. It's gotten ridiculous with the COVID. Now they don't even let you walk in the store. You got to go and You gotta place your order and go pick it up. Like it or not, our houses have turned into little prisons. Okay. So the next thing I want to teach you is solubility product. Now sometimes you have marginally soluble salts, meaning they're not very soluble, but a tiny amount of them does dissolve. And when you have things like that, you can use something called the solubility product to calculate just how much of this very slightly soluble substance dissolves into solution. And that's what we call the solubility product. Let me give you a brief definition of it. I'll leave some instructions in the part below the video, in the comments about which videos to watch to find solubility products. I didn't look it up before I started the video, so I'll find out for you and I'll write it in there. Solubility product is the product of the concentration of the ions involved in the equilibrium each raised to the power of its coefficient in the equilibrium equation. So I'll show you what that means. Suppose you want to show the solubility of something like silver sulfate. Now, silver sulfate is a marginally soluble salt. This is from page 741 of the practice example. Well, let's do an easy one first. Barium carbonate is also marginally soluble. It's a solid, but when you put it in water, a tiny amount of it dissolves. Most of it stays in the solid state. It doesn't dissolve, but it does have a little bit that is released. And it produces some barium ions, which are aqueous, and some carbonate anions, which are also aqueous. Small amount. So the K solubility product, the equilibrium of solubility, is given by the barium concentration at equilibrium. After you give it, and sometimes if you stir the solution for a while, a tiny amount of it will dissolve, and once it reaches that equilibrium, no more will dissolve. So if you multiply the two equilibrium concentrations at that point, they will multiply out to a number 5.0 times 10 to the negative 9. If you take something like silver sulfate, which contains 2 silver ions combined to sulfate, it also is a very marginally soluble salt. Not much of it dissolves in water, but when it does, you get 2 silver cations and you get a sulfate anion. Both of them aqueous, and where the KSP for that expression will be KSP equals the silver ion concentration to the power of 2 times the sulfate anion concentration. And if you multiply those two concentrations with the appropriate powers, you get 1.5 times 10 to the negative 10. In some substances, their KSP value changes with temperature. So you always have to pay attention to what temperature you're doing the experiment at, because KSP is subject to differences. Change the temperature, you change the value of K. So at each temperature you'll have a different value. And some substances become incredibly much more soluble at a higher temperature. And there are even some substances that decrease in solubility with temperature. So you have to look up the tables for whatever it is. Usually when they do mention KSP calculations, they say at 25 degrees Celsius, and the table at the back of the book is for everything at 25 degrees Celsius. There's a problem on page 742 where they ask you to do one of these. So I'll do it with you on the space that's left on the board, so called. So practice exercise on page 742. It says, a saturated solution of magnesium hydroxide in contact with undissolved solid is prepared at 25 degrees Celsius. The pH of the solution is found to be 10.17. Assuming that magnesium hydroxide dissociates completely in water and there are no other simultaneous equilibria involving the magnesium or hydroxide ions in the solution, calculate KSP for this compound. Okay, so here's what happens. I'm going to try to make some extra space on the board. Sorry for all the racing time, but we're going to need the space. Ooh, this time it worked. Maybe I should just stick to the straight up damp cloth with alcohol. Hey, that's what you call serendipity. Let's see if it works on the upper part of the fridge, which is cleaner. Oh, that's beautiful. I think I discovered the trick. You got to have a damp cloth. See, now let's look at this with a scientific perspective. How is a damp cloth creating an advantage? Well, there's water in the cloth. Guess what water can do? Hydrogen bond. You got it. So hydrogen bonding is going to allow the solvent, which is 99% alcohol, to lift up the marker, and then the damp cloth attracts the alcohol because there's a good interaction between ethanol and water. That's science at work, folks. That was just a thing of beauty. I might not have to buy that board after all. Mind you, I already placed the order, but there was a glitch in the order. I'm almost hoping it doesn't go through. Awesome. I love that. Made an accidental discovery. All right, so let's show how this problem works. It's got to be dry though, or else I'll wreck my marker. There we go. So this is the equation. This is from page 742 of your text. Practice example. So we're starting off with magnesium hydroxide, which is a solid. It is a marginally soluble substance. In fact, they used to use this as a remedy for excess stomach acid. You can eat this, and it's a strong base, but because of its low solubility, only a small amount of it is available at any given moment. So you can actually eat it and it won't harm your stomach, and it'll help readjust the pH of your stomach if you have acid indigestion. Also, there's a lot of magnesium present, so it's a laxative if you take a lot of it. So this is what you get. So magnesium hydroxide will dissociate marginally to give you one magnesium cation and 2 hydroxide anions. The KSP would be given by the magnesium concentration at equilibrium times the hydroxide ion concentration squared. And what's it asking? It's asking pH of the solution is found to be 10.17. So that's the one clue they give you. They tell you the pH from which you can calculate the OH minus concentration. We can rewrite this equilibrium as, if we let X equal the magnesium concentration, let's just make the statement, let X equal magnesium concentration. Therefore, we can say KSP is equal to X times 2 times X, because you're going to get 2 hydroxides, but you also have to write, your concentration of hydroxide is going to be twice the concentration of magnesium. So that's why you're going to say 2x, because for every equivalent of magnesium hydroxide that dissociates, you'll get 1 magnesium ion and 2 hydroxides. So that's going to be a 2x, but you got to raise it to the power of 2 because that's how the KSP is set up. So that simplifies to x times 4x squared, which simplifies yet again to 4x cubed. And 4x cubed equals your KSP. Now, let's find out what the OH concentration is. So, since the pH is equal to 10.17, the H plus concentration is equal to 10 to the negative 10.17, which gives you 6.760, 829, 75 times 10 to the minus 11. And we can use the water solubility product, Kw is equal to H plus concentration times OH minus concentration to solve for H plus concentration, for OH minus concentration. So OH minus concentration is equal to Kw over the H plus concentration, or 10 to the negative 14 over 6.67, etc., times 10 to the negative 11. What you get is an OH concentration of 6.760829 times 10 to the negative, no you don't, did the wrong one. Okay, what you get is 1.479 times 10 to the negative 4. So that's the OH minus concentration. So what you get is X is equal to 1/2 of that 1.479, etc., times 10 to the negative 4, which gives you 7.39554194 times 10 to the negative 5. So that's your magnesium ion concentration at equilibrium. And because that's also equal to X, you can write that KSP, which is what they're asking you to find. Because it's 4x cubed, you're going to say 4 times 7.395, etc., times 10 to the negative 5 raised to the power of 3. What you get when you do that is 1.6179 6828 times 10 to the negative 12, which you're going to reduce down to 2 sig figs. So you get 1.6 times 10 to the negative 12 as your final answer. That is the value of KSP for magnesium hydroxide under the conditions that they describe here. So that is how you do a KSP question. Why don't you tomorrow, or rather tonight, try the one on page 743. So for homework for this weekend, practice example on page 743. It's short. It's like literally 5 minutes of homework. See if you can get it. And we'll see you on Monday. Hopefully I'll have a good board by then.